In this video, we will solve problems from exercise 1.1. Question number 1. Write the following in roster form. So let's take the first one, which is x belongs to n. So when you say n is natural numbers, which are 1, 2, 3, and so on up to infinity, x squared, such that x squared is less than 121 and x is prime. So we have two conditions here. One, that x squared is less than 121, and the second condition is x is a prime number. So let's start working with the prime numbers. Now let's consider the smallest prime number, which is x is equal to 2. So x squared will be now equal to 4, and that's less than 121. So it satisfies the condition. So 2 has to be a member of this set. Then let's consider the next prime number, which is 3. So x squared is equal to 9. Again, that is less than 121. Again, it satisfies the condition. So let's take the next prime number, which is 5. And 5, x squared will be equal to 25. Again, it's less than 121, and it satisfies the condition of prime numbers. Then the next prime number is 7. Now x squared will be equal to 49, and that's less than 121. Again, that satisfies the condition. Then x is equal to 11 is the next prime number, and x squared will be equal to 121. But 121 is not less than 121. Therefore, your solution will be 2, 3, 5, and 7. Therefore, the solution is 2, 3, 5, and 7. Let's take the second one, which is the set of all positive roots of the equation x minus 1 into x plus 1 into x squared minus 1 is equal to 0. So you are given the condition x minus 1 into x plus 1 into x squared minus 1 is equal to 0. So when can you have this to be equal to 0? When x is equal to 1, then 1 minus 1 will become 0. So that this expression will become 0. Similarly, when x is minus 1, again this will become 0. So the expression will become 0. Now, for x squared, x can be plus 1 or minus 1. On both the conditions, it will be 0. So you have two solutions, which is x is equal to 1 or x is equal to minus 1. But we are given the condition that it's a set of all positive roots. Therefore, the solution is just 1. Minus 1 is a negative root. Therefore, 1 is the solution to this problem. This is the second problem. Let's take the third one. So for the third one, the expression is x belongs to n such that 4x plus 9 is less than 52. So x belongs to all natural numbers. So let's start the natural numbers from 1. So when x is equal to 1, 4x plus 9 will be equal to 4 into 1 plus 9, which is equal to 13. That's less than 52. If we take x is equal to, let's say, 3, then 4x plus 9 will be equal to 4 times 3 plus 9, which will be equal to 12 plus 9, that is 21. Again, it's less than 52. So let's take now x is equal to 4. Then 4x plus 9 will be equal to 4 into 4 plus 9, That is 16 plus 9 will be equal to 23. And again, that's less than 52. So let's take x is equal to, let's go for a bigger number. Let's say 7. Then 4x plus 9 will be equal to 4 times 7 plus 9, which is equal to 4 times 7 is 28. 28 plus 9 will be 37, which is again less than 52. Let's take x is equal to 10. Then 4x plus 9 will be equal to 4 times 10 plus 9, which is equal to 49. That's less than 52. If we take x is equal to 11, then 4x plus 9 will be equal to 4 into 11 plus 9, which is 44, plus 9, that will be 53. And 53 is not less than 52. Therefore, your solution is up to natural numbers from 1 to 10. So the solution is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now for the last one, to be written in the roster form, which is the given condition is x such that x minus 4 by x plus 2 is equal to 3, and x belongs to set of all real numbers minus the minus 2. So the given condition is that x minus 4 divided by x plus 2 has to be equal to 3. So let's simplify this. So x minus 4 is equal to 3 times x plus 2. That implies x minus 4 is equal to 3x plus 6. So further simplifying, if we take the x to the other side and 6 to the side, this becomes 3x minus x is equal to minus 6 minus 4. Therefore, 2x is equal to minus 10. That implies x is equal to minus 5. Therefore, since minus 5 is part of the set real numbers without the minus 2, the solution is minus 5. Question number 2. Write the set minus 1, 1 in set builder form. Right, so now we're given the roster form. We need to write it in set builder form. So look at it. We have a minus 1 and a 1. So minus 1 squared is equal to 1. And 1 squared is also equal to 1. Therefore, we can say in the set builder form, it is x such that x squared is equal to 1 and x belongs to set of all real numbers. Question number 3. State whether the following sets are finite or infinite. Question number 1. Question number 1 says, you're given a set x such belongs to n such that x is an even prime number. Now, only 2 is the prime number. So the set is equal to 2. Therefore, the given set is a finite set. Question number 2. You're given x belongs to n such that x is an odd prime number. Now that will be equal to 3, 5, 7, 11, and so on. The set is infinite. Therefore, the given set is an infinite set. Question number 3. You're given x belongs to set of all integers such that x is even and less than 10. So that would be 2. Now, since it's integers, you have negative integers and positive integers. So let's start from the right side. So you will have, it should be less than 10. So you have 8, 6, 4, 2, 0, minus 2, minus 4, and this go on up to minus infinity. Therefore, the given set is an infinite set. Question number 4. X belongs to R such that X is a rational number. So from this we can directly say that the given set is an infinite set. And the last one, which is x belongs to set of all natural numbers such that x is a rational number. Again, this will also be up to infinite. So the solution is the given set is an infinite set. Question number 4. By taking suitable sets A, B, C, verify the following results. So you can see A, B, C is in all the questions. So let's consider 3 sets. Let's take the set A to be 1, 2, 3. And we can take set B as, let's say, 2, 3, and 4. And we can, let's say, set C as 3, 4, and 5. Right. So first question is, we need to find A cross B, or rather prove that A Cartesian with B intersection C is equal to A Cartesian B intersection with A Cartesian C. Right, so let's take the left hand side and let's work on first B intersection C. So B intersection C would be, we have 3 and 4. Then A Cartesian with B intersection C will be equal to, our A is 1, 2, 3, Cartesian product with 3 and 4. And that would be equal to 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, 3, and 3, 4. Now let's do the right hand side, which is, our right hand side will be A cross product, A Cartesian product with B intersection with A Cartesian product with C. So let's first take A Cartesian with B, and that would be equal to, we can take directly from the sets here. So 1, 2, 1, 3, 1, 4. Then you have 2, 2, then 2, 3, then 2, 4, here, then 3, 2, 3, 3, 3, 3, 4. Similarly, A Cartesian with C would be equal to 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, and 3, 3, 3, 4, 3, 5. Okay, now we need to get A Cartesian product B intersection with A Cartesian product with C. So what are the common terms here? So you have 1, 3, which is common. So let's put 1, 3. Then 1, 4 is common. 1, 4. Then you have 2, 2 here, which is not here. 2, 3 is common. So 2, 3. Then 2, 4 is common. So 2, 4. Then 3, 3 is common. 3, 3. Then 3, 4 is common. 3, 4. Now you can clearly see that this set here and the left hand right hand side set here are both equal. Therefore, LHS equals RHS. Hence the proof. Question number 2. We have to prove that A Cartesian product with B union C is equal to A Cartesian with B union A Cartesian with C. So let's again take the left hand side. So our B union C will be equal to 2, 3, 4, and 5. And our A Cartesian with B union C will be equal to 1, 2, 1, 3, 1, 4, 1, 5. Then 2, 2, 2, 3, 2, 4, 2, 5. 3, 2, 3, 3, 3, 4, and 3, 5. Similarly, let's take the right hand side, which is we have to prove that the left hand side is equal to A Cartesian product with B union A Cartesian with C. So let's take A Cartesian B first. So that will be equal to 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. Next, we need to find A Cartesian with C, and that will be equal to 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 3, 3, 4, and 3, 5. Next, A Cartesian B union with A Cartesian C. That means all the items from 1 and 2 have to be put together. So we have a 1, 2, 1, 3, 1, 4, and you also have a 1, 5 here. 1, 5, then 2, 2, 2, 3, 2, 4, and the other 2, 5 in this 2, 5. Similarly, 3, 2, 3, 3, 3, 4, and 3, 5. So clearly we can see that our LHS is equal to RHS, hence the proof. Next is question number 3. So we have to prove A Cartesian B intersections B Cartesian A is equal to A intersection B Cartesian with B intersection A. So let's take the left hand side first. So A Cartesian B will be equal to 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. Then let's take B Cartesian with A. So that would be B Cartesian with A will be 2, 1, 2, 2, 2, 3, then 3, 1, 3, 2, 3, 3, 4, 1, 4, 2, 4, 3. Therefore, A Cartesian with B intersection with B Cartesian with A will be equal to all the common terms in both. So what are the common terms? So let's look for common terms. So you have 2 and a 2, which is common. Then you have 2 and 3, which is common. So let's start writing them down. 2, 2, 2, 3. Then you have 2, 4, not here. 3, 2 is common. So 3, 2, 3, 3 is common. 3, 3, and that's it. Now let's go to the right hand side. So in the right hand side, what we need to find is A intersection with B Cartesian product with B intersection A. So A intersection B will be equal to all the elements which are common to A and B, and they are 2 and 3, and B intersection A is equal to 3 and again it's 2 and 3, or I can say 3 and 2, right? So now A intersection B Cartesian product with B intersection A, so that would be equal to 2, 3, 2, 2, 3, 3, 3, 2. So clearly we can see that our LHS is equal to RHS, hence the proof. Question number 4. So in question number 4, you are given to prove C minus B minus A is equal to C intersection A union with C intersection B dash. Now we have a B complement. So for B complement, we need to have a universal set. So let's define our universal set U as 1, 2, 3, 4, and 5. Right? So now let's take the left hand side. So we need to prove C minus B minus A is equal to this. So let's do B minus A first. So what is B minus A? All the elements which are in B, but they should not be in A. Now 2 is in B, but it's also in A, so 2 is removed. 3 is in B, also in A, so you need to remove 3. 4 is only in B, not in A. So your answer is 4. Similarly, C minus B minus A will be equal to all elements that are in C but not in this B minus A. So 4 has to be eliminated. So your answer will be 3, 5. Now let's take the right hand side. So in the right hand side, we need to find C intersection A and union with C intersection B dash. So let's take C intersection A first. So that will be equal to, what are the elements which are common to C and A? That's only 3. Similarly, before we find C intersection B dash, we need to find B dash. B complement is items that are not in B but in the universal set. So 2, 3 and 4 are in B, and so we need to remove them from the universal set. So it's 1 and 5. So your C intersection with B dash will now be equal to elements which are common to C and to B dash. So the common to C and B dash is only 5. Therefore, our C intersection A union with C intersection B dash will be equal to 3, 5. So we can clearly see left hand side is equal to right hand side, hence the proof. Question number 5. So we have to prove that B minus A intersection with C is equal to B intersection C minus A, and that is equal to B intersection with C minus A. So let's take each term. So first, let me take B minus A intersection with C. So first we need to find B minus A. So items which are in B but not in A will be 2, 3 are in A, so remove them. So 4 is your answer. Then B minus A intersection with C will be items which are common to both B minus A and C. So that's only 4. Now, the second part of our question is to show that it's also equal to B intersection with C minus A. So let's first find B intersection C. That's equal to, what are the items which are common to both B and C? It's 3 and 4. Then B intersection C minus A will be the items that are in B intersection C but not in A. So 3 is in A, so remove 3, so you are left with 4. Then for the last part of it, which is B intersection C minus A, so let's first find the C minus A, and that will be equal to items that are in C but not in A. So 3 is in C but is also in A, so 3 is eliminated. 4 and 5 are in C, not in A. So the answer is 4, 5. Next, B intersection with C minus A will be equal to the items which are common to C minus A and B. So 4 and 5 is in C minus A, 2, 3 and 4 are in B, so the items which are common are 4. So let's call this as 1, and this as 2, and this as 3. Therefore, from 1, 2 and 3, we can say that B minus A intersection C is equal to B intersection C minus A is equal to B intersection C minus A. Hence the proof. Question number 6. we have to prove B minus A union with C is equal to B union C minus A minus C. So let's take the left hand side here. That is B minus A union with C. So let's first find B minus A. So B minus A, we have already found that to be 4. And B minus A union with C will be equal to 3, 4, and 5. Let's go to the right hand side now. So the right hand side is, we need to find B union with C minus A minus C. So let's find what is B union with C. So B union with C is all the elements which are in both B and C. So that is 2, 3, 4, and 5. Similarly, A minus C will be equal to items which are in A but not in C. So 3 is the common item. So let's remove 3, that's 1 minus 2. Next, B union with C minus A minus C. So all the items that are in B union C, but they should not be in A minus C. So 2 is common to both. So remove 2 from B union C, your answer will be 3, 4, and 5. Therefore, LHS equals RHS, hence the proof. Thank you for watching Maths Tutorial Anand. Please like and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.